Welcome to part 2 of this video, in which we are computing the energy and power for discrete time signals. In part 1, we went through x is the unit step function, and then we also went through the case where x is a decaying exponential that starts off with a value of 1 at time 0, and then as n increases, it decreases by a factor of 1/2 each time. So the next one we'll do is this one, where x is e to the j pi over 4n. Okay, so let's bring up a blank page, and we have x of n is e to the j pi over 4n. Okay, now in order to find the energy, we need to sum from minus infinity to infinity the magnitude squared of xn. Okay, now it turns out in this case this actually is a complex number, and so the magnitude squared means more than just simply taking x and squaring it. To get the magnitude squared, we take to get the magnitude squared of a complex number, we take the number, which in this case is x of n, and we multiply it by its conjugate, which is usually represented by a star. And you get the conjugate of a complex number by changing the sign of the j everywhere it shows up. So xn is going to be e to the j pi over 4n. X conjugate n is going to be e to the minus j pi over 4n. Okay, so again, the conjugate came, this star here just means that I changed the sign of j. Now when I multiply these two guys out, I have e to an exponent times e to another exponent. So this is going to be e to the sum of the exponents, j pi over 4n minus j pi over 4n. This term minus this term is 0, so the whole thing is e to the 0, which is just 1. Okay, so what this says is the magnitude of this complex exponential is 1. Now there's other ways of showing that. One way, which I won't go into, is you know that e to the j pi over 4n is cosine pi over 4n plus j sine pi over 4n. So again, you could square things and find out that the magnitude is indeed 1. So what that means for this computation, the energy computation, is every term in the sum is going to be 1. And so if I sum from minus infinity to infinity, that means that I'm going to have an infinite number of 1s in my sum, and the answer is going to be infinite. So this is not an energy signal because the energy is infinite. Because the energy is infinite, we might think that this is a power signal. So let's check that out. So we have the power signal, or the average power, is the limit as n approaches infinity, 1 over 2n plus 1 summation, and going from minus cap n to cap n of the magnitude squared of xn. Now again, we know that this guy here is 1. And if we look at how many terms are in the summation, n starts at minus n and goes from minus n to minus 1, so that's n terms. Then there's a 0th. When n is 0, that's 1 term. And then going from 1 to cap n, that's another cap n terms. So the number of terms I have in this summation is 2n plus 1. And I have each term in the summation equals to 1. So if I take 2n plus 1 ones and add them all up, I get 2n plus 1. So I can write this then as the limit as n approaches infinity of 1 over 2n plus 1, and then this sum here, which is 2n plus 1. And basically this guy will cancel this guy, and I'm left with just the limit of 1, which is 1. Okay, so what this tells me is that the energy is infinite, the average power is 1, which makes sense because every term in this summation, actually I guess down here, every term in this summation has a value of 1, and I'm basically dividing here by the number of terms in the summation. So if every term in the summation has a value of 1, I add things up and then divide by the number of terms in the summation. It works out to be 1. Okay, so hopefully that makes sense. We've got one more. Let's see, we've finished this one. So the last one we have to do is x of n is cosine pi over 6n. So let's bring up a blank spot, and we have x of n is equal to cosine, oh this is bad, pi over 6n. Okay, so first we want to find the energy, and this is going to be the sum n going from minus infinity to infinity of the magnitude of x n squared. Now the xn we have here is entirely real. There's no imaginary part. So all we have to do is take x of n and square it. So each term here will end up looking like a cosine pi over 6n, and the whole thing squared. Now, to make this easier to evaluate, we're going to use the following trig identity. The cosine of something squared is 1/2 plus 1/2 times the cosine of that something, in this case pi over 6 times n, times 2. Okay, and so I can write this now as pi over 3n. So what I have here is that I'm summing n going from minus infinity to infinity of 1/2 plus 1/2 cosine pi over 3n. Okay, well, we're almost done. We just need to do, we need to look at one more thing associated with this cosine of pi over 3n. If I were to graph this, so as a function of n, I have when n is 0, this cosine has a value of 1. When n is 1, I have the cosine of pi over 3, which, if I remember correctly, is something less than 1. When n is 2, I have the cosine of I have the cosine of 2 pi over 3, which turns out to be the negative of this guy. And when n is 3, I have the cosine of pi, which is the negative of this guy. And then when n is 4, I get the cosine of 4/3 pi. When n is 5, the cosine of 5/3 pi. And when n is 6, I'm back here to a value of 1. And so it turns out this term is the negative of this term. This term is the negative of this term. And this term is the negative of this term. So when I take this cosine and sum it over one period, which in this case is 6 samples, the sum of this cosine over 6 samples is 0. Okay? And if I look then at another 6 samples, so going from 0 to n equals 5, this cosine sums to 0. If I look at the next 6 samples, again the cosine will sum to 0. And so what that means is, because I'm summing over all possible values of n, every group of terms in the sum of 6 of these guys of 6 consecutive of these guys is going to be 0. So what that means is that we have the energy as the sum n going from minus infinity to infinity of 1/2, because this term here is going to average to 0. Okay. Now the sum from n going from minus infinity to infinity of 1/2 is still infinite. Okay. Anytime you take an infinite number of 1/2s and add them up, it's infinite. But an interesting thing happens when I go to compute the power. Okay, when I compute the power, let's see, we have P is the limit as n approaches, as cap n approaches infinity, 1 over 2n plus 1 times the summation n going from minus cap n to cap n of the magnitude squared xn. Okay. And what we find, again, this term here looks like this. It's got a half, and then it's got a 1/2 cosine of pi over 3n. And so as I sum these guys up, they tend to go to 0. Okay, at any given time, or for any value of cap n, I'll have something here that's not exactly 0. If I sum from little n going from minus cap n to cap n, if I'm summing these guys, I'll have something that's not exactly 0, but it never gets bigger than 1, if I recall correctly. And in addition, I have this 1/2. So these guys will end up averaging each other out, and I'm left then with just the 1/2. So the terms here are going to be 1/2, and in the sum going from minus cap n to cap n, I'll have 2n plus 1 of them. So what I end up with then is 1/2 times this value divided by this value. So the whole thing is just 1/2. And then I take the limit as cap n goes to infinity, but this doesn't depend on cap n. So there you have it. The average power of this cosine is 1/2. The energy, the total energy, is infinite. Okay, so hopefully you've noticed a couple useful things. One is that if I have a finite energy, then my average power is 0. The other is if I have a non-zero average power, my energy has to be infinite. And the third is that I can actually compute what that average power and what that energy are by actually summing all the terms in the in x of n and seeing what I get. So hopefully you found this useful. Thanks for watching.